Yes. Okay, next page. See the effect of damping. If your damping equal to the critical damping, this is the frequency response. At the resonant frequency, see, critical damping, there's no apparent peak, but for low damping, the peak goes higher and higher at the resonance frequency. So this is the effect of damping to the system. Damping is the same as resistance. Low resistance, you got flat response. Sorry, low resistance, you got high peak response. There's an overshoot. But high resistance, the overshoot becomes smaller and smaller. Okay, next page. Another example. If you have a mass M, you have a car. You drive your car and you put a mass on top of your car. And the mass connected to the roof of your car by a spring K and a damper B. So you could think you sit in the car, you watch this mass going up and down. We use this coordinate Z. So Z, the origin of Z is the car, not the ground. So Z is Z start from the car. And Y represent the coordinate of M, the mass. We assume the displacement M greater than Z, because when you drive your car, the ground might not be flat, so your car might go up and down, up and down. So that's the displacement of Z. Then, in terms of this spring K, if Y greater than Z, then the reaction force from the spring is K times Y minus Z. And the damping is the velocity, relative velocity. B, Y dot minus Z dot. And based on Newton's second law, camera stop. Thank you. So we do change of the coordinate. We set x equal to y minus z. Then x dot, x double dot. Then y double dot, you can remove this one. Then replace, put them back to this equation. You can get this new equation. mx double dot plus bx dot plus kx equal to minus mz double dot. And z is the deformation acceleration of your car. Z, the input, and x represent the relative coordinate y minus z. And if z equal to z sine omega t, sinusoidal input, then z dot, z double dot, you can get this one. You put this one back to the equation. So mz, capital Z is the amplitude of this input. The amplitude, omega squared sine omega t. So mz omega squared, you could take this one as the force, Fo, and sine omega t. Okay, next page. Then we move m. We divided each term by m. Then remember, b over m is 2 zeta omega n. K over m is omega n squared. So we put omega n square root k over m, because this one equal to this one. Then b over m, 2 zeta omega n, 2 zeta omega n equal to square root k over m. Then we say b now equal to 2 zeta omega n. We can use this one and this one. We can get b value here. Okay, this is critical damping ratio. We define Vc equal to 2 square root Km. So this is the critical damping ratio. If B equal to Vc, then zeta equal to 1. Critical damping. Okay, next page. See, zeta is B divided by Bc. Then Bc is 2 square root Km. Then we assign this value to be 1 over 2Q. Q is the quality factor. The definition is the same as the electrical system. They are equivalent. So the damping ratio equal to, you can use this equivalence to calculate this value. Now, come back to this equation. So M equal to K omega N squared. Omega N squared K Fext. So if the external force is 0, we can do Laplace transform to this equation. Remember, Laplace transform for differentiation equal to x, capital X, minus initial condition of x. And x double dot equal to x squared, capital X minus x, x prime 0, initial velocity minus initial displacement. So this is the equation for Laplace transform. Next page. Okay, but we assume initial position 0, initial velocity 0. Then this is the form we use Laplace transform. Then for this characteristic equation, we can get the roots for the characteristic equation. We can get these two values. Okay, now, if Fext is not 0, again, Laplace transform. And we can get transfer function. X is the displacement. We take that as the output. Fext, the force, is input. Output, input. So this is transfer function. So this is the transfer function. Then M can be transformed into this. Then we can, this is a transfer function. We can assign S equal to J omega. Then we can get this final form. Okay. Although now I won't ask you to do the derivation in the class. If you are a diligent student, you should spend your own time to derive all of them to practice. Then you will be good in this. Next page. Okay, transfer function. This is the amplitude of the transfer function. So we take absolute value of this one. And x is the amplitude. Say you say x0. Fext amplitude Fi here. Then we transform this one into this one. Then, okay, some review of complex number. Z is a complex number, A plus Bi or A plus Bj. Real axis, imaginary axis. A is the real part, B is the imaginary part. And this one is the phase angle. Phase angle arctangent B divided by A. So phi is the phase angle, the transfer function. This is transfer function, and this side represents phase angle. And phase angle equal to, for this one, phase angle of 1 is 0. And this is minus arctangent. This is real part. This is imaginary part. So that's why we have minus sign here. because we take transfer function phase angle based on this one. Or previous page, based on this one. We have real part, imaginary part. So we do phase angle, then the numerator phase angle is 0 minus the phase angle of the denominator. Next page. So the phase angle of the denominator. This is phase angle of the numerator. Remember, minus sign here. Next page. Okay, so those are the background of these accelerometer equations. See, this is familiar. We drive a car, and the mass M is the accelerometer. So the accelerometer, x is the coordinate of the accelerometer relative to the driver, not to the ground. And Fext is z omega square. See, F0 is sine omega t. F0 should be the displacement of the car times omega square. Okay, then we put m. We divide each term by m. We get this equation. So if you, these two equations are in the previous PPT. Again, transfer function, this one. Transfer function, the amplitude. You can use this command. This is amplitude. This is phase angle. Okay, so we got all of them covered. Any question so far? Any question? Okay, next page. So this is the frequency response. See, this is the logarithmic scale. This is phase angle. And this is frequency ratio. So frequency ratio equal to 1 means this is resonant frequency. This is resonant frequency. And the phase angle dropped to 90 degrees because it's a second order system. So the phase, when omega is large, the phase angle is minus 180 degrees. And we have the overshoot, this one. For small damping ratio, 0.01, the overshoot is large. But for, if the damping, critical damping is getting large and large, then see, there's no overshoot. Okay, next page. Step response means we move, we give a step input. Okay, we can, I guess, we can, okay, for oscillator, Q is large. But for accelerometer, Q is small because we operate the accelerometer in the air. We have air damping. So the Q value for accelerometer is small. But for oscillator, we try to decrease the damping because we want the device to oscillate. So we need to have large Q value. Then, okay, step response. See, this is 1, this is 0. So we just say we apply a force, like unit force, and we want to see the response. Then it takes some time to go to the final result, 1. Then we have the ringing. So we just zoom in. We can see the reading. It takes a lot of time to reach the final value. Okay, next page. So again, yeah, the car, the M, X, Y, and T, and the free body diagram. So we have done this already. So we just skip this one. Then the frequency response. Okay, we can skip. Okay, we can skip again. Okay, example 1. Previous. See, this is frequency. S equal to J omega. At low frequencies, this one disappear, this one disappear. We are left with Kx equal F. And F is the ground acceleration. Okay, next page. Previous. See, when frequency goes to 0, remember S equal to J omega. If omega is 0, low frequency, omega goes to 0. Then the first one and the second one disappear. Then we have the K. So Kx equal to F. You can M can bring here. MAN is the external force, and Kx equal to MAN. Remember, we have mz omega square. So that's why we have this equation, x equal to m divided by k multiplied by an. Okay, previous. See, based on this equation, we have this one. And y double dot. See, this is y. And y double dot is the acceleration of the car, because we want to measure the acceleration of the car. So m is the accelerometer. So y double dot is the acceleration, an. And at high frequency, at low frequencies, 0, 0. Kz equal to m times acceleration. So Kz equal to m times acceleration. We take absolute value, so we can ignore the minus sign. Kz m y double dot. So z equal to m y double dot divided by a equal to man divided by k. Next page. Next. So that's why we have this one. Next page. And that's why we have this one. So for this case, we have an accelerometer. The displacement x, you see in the car, then you measure the displacement of x, the accelerometer. So the displacement is 0.5 micrometer. And the acceleration is 2g. So a is acceleration, 2g. G equal to 1g is 9.8 meter per square second. And omega n, because now the frequency, we want to know the frequency omega n. Omega n equal to 2 pi f square. So using this equation, you can calculate this value. Okay, now practice your calculation. Use your hand calculation. Yeah, write your solution. Camera off. Now we have another example. We have a spring constant, K, 1 Newton per meter. So we know the K value, and M equal to K divided by omega N squared. Because for a spring, omega N, the resonance frequency equal to square root K over M. So we have this equation for any spring under vibration. Now we know K value, and we know the resonance frequency 2 Hertz. So now you can use this relation to calculate the mass M. 2 Hertz, because omega equal to 2 pi F, F 2 Hertz, K equal to 1. Then use this equation, you can get this value. So this is mass. Then we can estimate the volume, because if the material is silicon, the density of silicon is 2.33, 10 to minus third kg per cm cubic meter. Then the dimension, assume it is a cubic. So L cube equal to M. L cube is the volume. Volume equal to mass divided by density. So mass divided by density. So we can estimate the size of the cube. This is very large, 1.4 cm, because cm is not easy to imagine, difficult to imagine. Next page. Okay, so for beam, cantilever beam, if we apply force F, we can get displacement D. And at the end of the beam, there's a tangent. The tangent of the beam to the horizontal, we get angle theta. So kappa is the curvature of this beam. Assume this one looks like an arc. So kappa curvature equal to y is the displacement. This is y. So y differentiation twice with respect to x. This is x. Equal to moment m divided by EI. And moment equal to F times D. The moment applied to this cantilever beam. Then the maximum displacement D equal to this equation. If you know the force F you applied, you know the length L, you know the Young's modulus E, I is the second moment of area of the beam. So I equal to width times thickness cubic divided by 12. It's okay, you can check this value later, or you can ask Hugh, what is I value for a beam? And this one for one end fixed, the other end free. And for another case, one end fixed, the other end we have a slider. So the angle theta is 0. For this case, this is displacement and this is force F. The relation is a little bit different. Next page. Then in micromechanical system, we have many different structures. We have this type of shuttle mass, anchor, or shuttle mass, anchor, or this type, or this type. Different structure has different spring constant. Okay, next page. So again, accelerometer MAN equal to KX. Okay, then this is sensitivity of an accelerometer. This is capacitive type. Capacitive type, we use capacitance to measure the output of the device. So for our accelerometer, input is acceleration, output capacitance change. then AN equal to X omega N squared. We can estimate the capacitor, the shuttle mass displacement X, and the resonant frequency omega N, and C. So 9.8 comes from the G value because this is meter per square second, but we want to use the unit G. So meter per square second divided by 9.8, we can get G value. But we move 9.8 to the denominator. And C0 is the initial capacitance of your accelerometer. It's just an estimation. We just estimate the sensitivity of the accelerometer. C, delta C is the capacitance change. And capacitance change equal to epsilon A. So let me do the math. Okay.
Okay.
Next page. Next. Okay, let me do the math. C delta C equal to epsilon A divided by D minus epsilon A D plus delta D. So this is the original one. This is the new one. Because for an capacitor, original gap is D, and this one is fixed. So if the gap change to D plus delta D, the new gap between two electrodes, this is electrode 1, electrode 2, electrode 1. So electrode 2 move a distance delta D. Then we can use the approximation epsilon A divided by D. Remember epsilon A, this is D plus delta D minus first order. So epsilon A divided by D minus epsilon A. We can put minus 1 inside D minus delta D. Okay, maybe I don't need to do this. I'll start. So we should do, say, D epsilon A minus epsilon A, D plus delta D. Then we do this D plus delta D. Epsilon A move to the front. This is D plus delta D minus D. So D minus D cancel out. And epsilon A delta D, and the denominator is D squared plus D delta D. But D squared is much larger than D delta D. So we can ignore this one. So epsilon A divided by D, this delta D divided by D. So epsilon A divided by D is the original capacitance. Then delta D divided by D. But I don't think the engineer, they did a good job here. So let's just forget about their derivation. It's just an approximation. So let's forget about it. Okay, next page. Okay, so this one. For accelerometer based on capacitance change. This is one capacitor. So this one can move up and down. And this one can move up and down. So this one is fixed. This one can move up and down. Then we have capacitor 1, 2, 3, 4. And for this type, so these two fixed, and this electrode can move up and down. For this one, fixed, 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 and this one can move up and down. This case will be in your, because after this lecture, you will do the layout for an accelerometer. For that accelerometer, they use this type of capacitance change. So this is, so they fix this one, they fix this one, they fix this one, and this one can move up and down. So for one finger here, they have two electrodes. One electrode, the other electrode. And now, look at this one. So when this one moves down, the capacitance of this one decrease. The capacitance of this one increase. So if you put this one, so this one is here. So epsilon 0 is the permittivity. L0 is the length. This one, overlap length, and T is the thickness. So epsilon 0, L0 T is the electrode area. And X0 is the initial gap. If this one moves down, the gap here increase, okay? And the gap for this one decrease. So delta C equal to this one minus this one. So C, this one minus this one. So if we do the math, this one minus this one, you can get this equation. But X0, X squared is very small. This is initial gap. Displacement is very small. So we can ignore this one. So this is the final result. So this is differential type of accelerometer. We have two main sensors. Main sensor 1 decrease. Main sensor 2 increase. So this is the principle of differential accelerometer sensing. Okay, next page. Okay, that's the detail. So fixed. The short, this electrode move up. So the gap, original gap. The new gap minus new gap plus. And C0. So this is the new capacitance is this one. The new capacitance is this one. Let me do this to be clear. So C0 is this one. Epsilon A divided by X0. And for this case, the new capacitance is epsilon A X0 minus X, delta X. And we can epsilon A. For this one, we move X0 out. So 1 minus delta x x0. But epsilon a x0, this one, equal to C0. Then this one is x0 minus delta x. So we move this one to the denominator. So we get this final one. So Kaiser, do you follow me? And for this one, similarly, we can get this new capacitance. So see, Vm is the modulation signal. So Vm minus Vm. So this one up and down, this one down, up. The modulation frequency. Cp is the parasitic capacitance. And this is the output V sense. So S V sense. Then Vs V sense. Vm is the modulation voltage. Then we can get this one. So they use KCL law. Current goes in. So this is the voltage divided by 1 divided by Cs. 1 over Cs, the impedance of the capacitor. Voltage difference divided by impedance is the current goes in. Vs minus M. Okay, current goes out. And Vs minus Vm. So current goes out. Current goes out. And this one is current goes out. Vs, this is ground. Vs divided by 1 over SCP. So current goes out, current goes out, current goes out. So based on KCL, Q curve, current law, this one should be 0. So based on this one, we can get this one. Okay, do this derivation by yourself, everyone. Camera off. Okay, so for this one, VSVN equal to this equation. But delta x equal to MAN divided by K. And move M to the denominator. K over M equal to omega n squared. Then for this one, the sensitivity, we define sensitivity Vs, output voltage, divided by acceleration An. So combine delta x here, put it here. You can get this equation. But the wire connection for this one, it says it has, okay, we can ignore this one. Okay, then for this circuit we only use 2, 1, 2. And this circuit we use 4 capacitors. So this one here and here. And this one here, one here. And capacitance, parasitic capacitance. This one and another one here. Then V sense P, V sense N. So now, based on this one, please derive this one. Okay, try. So Vs can be say V sense P minus V sense N. But hello, Vs equal to one of them. The difference between these two is Vs, okay? So derive this one by yourself, please. Based on the result here, then derive this one. This is differential. Okay, you can work this out by yourself in your free time. Next page. Kaiser, could you read this?
Variable gap capacitors are the most widely used electrolyte type for detection of small displacements.
Okay, for example, this is stationary electrode. This one is moving electrode. Coordinate is Y, goes up. Capacitance of this capacitor equal to epsilon 0, the vacuum permittivity. Epsilon R, relative permittivity, relative to the vacuum. So we call this dielectric constant, epsilon R. A, area, D, gap. So delta C. So now if they put epsilon 0 A divided by D, D is the original gap. This is C0. The new C is, now it says this one get closer. So if this one get closer, we do D minus Y divided by A. So you just imagine this one, the gap gets smaller. So you do difference, epsilon A, D minus Y, dy. So remember D squared minus YD, but YD is very small. So you can ignore YD, just keep D squared. For U18, D 2.3 micro. D is 2.3 micro. Okay, next. Okay, so this one is the case you are going to work on. Create a layout for this type. So the stationary, and this one is the moving electrode. So we anchor. So anchor means they are fixed. Anchor. So this one can move. So we have capacitance. Overlap is L0. And X0 is the gap. And T is the thickness. And this one is the total length of the finger. But this word is not perfect. We have capacitance here, but remember, say this is V minus, this is V plus. V plus, V minus, we have capacitance. But see, V plus, V minus, we also have another capacitance here. So here, lie. The reason I ask you just to create electrode here and electrode here is we don't want this straight capacitance. So the capacitance is L0 is the initial overlap. T is the thickness. So L0 times T is the electrode area. And X0 is the gap. Okay, next. Okay, again, the same. L0 overlap, T thickness. X0 initial gap. Next. Okay, this is the type. See, anchor and anchor. So this one can move. So C, we have one C here, the other C here. The one capacitor, the other capacitor. And now they are all capacitors. So if this one, initially at the center, move to the left, x0. So the new gap for this one is x0 minus. So x0 is the initial gap. And if this one move to the left by amount x, the new gap is x0 minus x. The new gap for this one is x0 plus x. So for the left capacitor, CL, this is the new capacitance. For the right capacitor, this is the new capacitance. So initial one here, the total capacitance, left capacitor, right capacitor, plus fringe. So this is fringe capacitance. Next. Yes, so this one, see this one is the comb can move, and they are all the same equations, similar equations. So initial one, the new one, and the difference, it times n, because for one finger, n is the total number of fingers. Next. Okay, next. 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 Sorry, previous. So if for U18 MEMS process, we have 1 poly and 6 metal. And this light blue is oxide. So after we finish CMOS process, we etch oxide first. After that, we etch silicon. So see, we have under etch. Supposedly it should be all silicon. But due to this etching process, some silicon under the anchor will be etched away. So this will affect the boundary condition of the anchors. For those mechanical engineers, they assume here the anchor cannot move at all. But in reality, anchor will move a little bit due to this under edge. This is inevitable. So that's why we need to keep the anchor as large as possible. If the anchor too small, if your anchor just like this, and part of it is etched away, then your anchor is not stable. So that's why we need to have large anchor. Next. See, we have metal 1 to metal 5 and metal 6. And this one is rotor. So rotor electrode and stator, rotor, stator, rotor. Okay, next page. Sorry, previous. And STI oxide. Okay, next. So this is a problem. We use white light interferometer to measure the curl of the mechanical structure. So the unit is, say, let's take a look at this one. So if this is anchor, due to the curl, this one will go this way, this one will go this way. See, your electrode will look like this. This is a problem. So that's why we need to design this way. So see, this one goes here, and this one goes out, then goes back. So in this way, they will curl together. So this one goes up. This one goes up together. So they will look much better this way. So this is a better design. So for mechanical engineer, when they design the fingers, they try to avoid one anchor here, one anchor here. Try to put all anchors on the same side, at the same side. This one goes up. This one goes up. Okay, next page. Brownian noise. The mechanical structure and air, but we have many molecules in the air. We have many molecules in the mechanical structure. Even there's no acceleration, we have some tiny vibration due to the air molecule motion and mechanical structure molecule motion. So this is Brownian noise. Akan, read this, please.
Mechanical noise is in a transfer is Brownian noise, which is from the random motion of gas. Electricity sound during the tools.
You should also study Voice of America.
Okay.
So for noise, we have electrical noise, but we also have mechanical noise. Mechanical noise due to vibration. For electrical noise, we have flicker noise. We have 1/F3 noise. We have thermal noise too, due to the resistor thermal noise. For mechanical noise, this Brownian noise, so we can use this equation to calculate equivalent voltage noise, because we want to convert mechanical signal to electrical signal. So this is temperature. So this is damping. R is damping. KB is Boltzmann constant. And T is absolute temperature. So we use this one to convert to equivalent voltage noise. Then C, R is damping, B, and T, the same here. And this is acceleration, this is mass. And this is equivalent voltage noise. So you put Vn, you move Vn here. So take square root. Vn, this is RMS value. So square root, this one. Then Bm, we can use our mechanical equivalence. Omega n equal k over m, and q is the quality factor. In our PPT, you can find the relation between q and km omega n. So you can turn this one into this one. So A is this one. And this equation here, because we want to change acceleration here, the unit here is meter per square second, but we want to use g, so we just divide it by 9.8. Okay, now derive this one, and for the Bm omega nq, look into the PPT in the previous page, and try to convert this one into this one. So here you can look for, you can copy those equations, relate to Bm omega nq. Yeah, please go to the previous PPT. Camera off. Okay, so for example, if the Q of your accelerometer is 0.2, the mass of your accelerometer is 1.85 micro kg. Remember, K is 10 to third, micro is 10 to minus 6. Okay, anyway, kg, micro kg, the frequency of the device is 0.74 kHz. Please calculate the Brownian noise based on this equation. Here is the hint for your calculation. So please calculate this value to make sure you have the ability to get the right answer. Camera off. Next page, please. Okay, now we have an example. So this is the differential accelerometer. We have C plus delta C, C minus delta C. This is the AMP amplifier. Then this is modulation voltage, modulation signal with high frequency. And demodulation, we lower the frequency. And another amplifier. So this is the total gain is AV. This is output voltage. So we have feedback capacitor. Feedback capacitor. Then this is resistance R. So we did the calculation here. Vm minus 0 divided by so this is C plus delta C here, C minus delta C here. So 1 over SC is the impedance, capacitance, resistance, impedance. So at this point, Vn, so we take this one. If we take this one as the ground, 0. You take this one as 0. So this is the current. And current, so this CF, so this is the impedance. Current current goes through this one, goes here. So this is the voltage at this point, A. And Vm minus 0 divided by the impedance is the current. Current goes through here and goes to Vb. So this is Vb. Va minus Vb. So VO1 here. VO1 is the voltage, Va minus Vb. So please convince yourself based on the equation here and this one. See if you can get the result, this one. So because we assume the frequency, hello everyone, we assume AC high frequency. For high frequency, this one has much smaller impedance. So the signal goes through this one. The signal won't go through this R. So you can ignore R for AC. Okay? Camera off. Then we have this example. Delta C, 1.5 femtofaraday per G, and feedback capacitance 100 femtofaraday, and modulation voltage amplitude 1.8 volt, the U18 MEMS process, and VO1 output voltage 54 millivolt. So you can use this equation to get VO1. After you get VO1, the output volt, if you sense the V out is 300 millivolt, 300 millivolt divided by 54 millivolt is the AV value, the gain value you need. So if your VO1 is only 54 NV and you want your output voltage to be 300 NV, you need to design your amplifier. The gain should be 5.6. Okay, next page. Okay, the output noise. Let's ignore this one. Next page. Next. Okay, for the result. So for U18 MEMS process, you get maybe 10 or 20 chips from the U18 MEMS. And this is the, they use the laser sensor to measure the frequency response, displacement versus frequency. For the 20 chips, the results are quite similar. And if you measure the omega n frequency, omega n equal to 4600 Hertz, you can change to omega n 2 pi f omega n. And the acceleration A and X is the vibration amplitude, 0.60862. So this is vibration amplitude X. Omega n here, we can estimate the input acceleration to be 47 G based on this figure. Next page. So this is the experiment in TSRI. Next. So for the accelerometer, everyone, because this is an accelerometer, this is the most important figure we need to get. We measure acceleration, and this is output voltage. So for any sensor, this is the most important one to show to me. Acceleration and output voltage, the linear response. This one is the spectrum of your accelerometer, frequency, then admittance. Admittance is similar to the transfer function. So we have this one is the frequency output. Because we test our device previous. This one, we shake our device. This is accelerometer. We put an accelerometer here, commercial one. So this accelerometer can measure the acceleration of the shaker. And we shake this device 100 Hertz. Next page. Okay, sorry, previous. Okay, sorry, next. So at 100 Hertz, you can get a peak of the output. But you have noise at other frequencies. Okay, next. 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 Okay, so that's all we will do for this lecture. Camera off.